So the subject of this lecture is not a long one, but it is nevertheless an important one because it will tell us something really meaningful about the way that we model large systems. And the conclusions that we're going to draw from this lecture are not just conclusions that we are going to use in the future, but which are going to retroactively apply to systems that we've studied in the past. And although it doesn't seem like we studied large systems in the past, you'll see where the connection comes in. Okay? So, to start us off with a practical example, let's suppose that you are a gardener or somebody who cares about agriculture, and you have some little slab of garden with surface area AS, which is exposed to air at some asymptotic temperature T air, that there's some heat transfer coefficient between your garden and the air of H, and that below, right, the surface of the soil where you're actually planting your flowers, that you can model the soil below it as kind of this infinitely long like slab of just earth, that as you go further and further down into it, eventually reaches some asymptotic temperature T soil, the same way that as you go further and further up into the air, you reach this asymptotic temperature T air. Okay, so the temperature over here is not going to be, T soil or TS. It's going to be somewhere in between, at least we think so. It's only as you get further and further down that you eventually reach T soil. And so you have this setup, and that maybe you're interested in trying to figure out what the temperature of the surface of the soil is as a function of these asymptotic temperatures and the material properties, right? H and K. So how do we study a system like this? Well, does it satisfy the four assumptions that we would need to satisfy in order to model this with a thermal circuit? Sure seems like it. Heat transfer is one-dimensional in the sense that all of the heat transfer is happening either upwards or downwards, right? From the soil to the air or from the air to the soil. So that works out. The material properties seem to be constant numbers, so that's good. We can assume that everything here is in steady state. So that also works out fine too, right? That these temperatures are just constant in time, that everything is constant in time, and that there's no heat generation anywhere in here, okay? And if we have these four assumptions, then it stands to reason, why don't we just model this as a thermal circuit? And in fact, we can. All that we have to do is model this as a series thermal circuit with two elements, the soil and the air. So what are the temperatures? Well, temperature, all the way up at the end of this convective thermal resistance is T air. This temperature is TS, and this one is just T soil. Because this is a convective thermal resistance, it's easily expressible as just 1 over HAS. No issues there. It's the same thing that we've done all the time. However, what about this, right? This is a planar conductive thermal resistance. And because it's a planar conductive thermal resistance, it has the same form as every other planar conductive thermal resistance, which is delta X over Ka. And here is where the problem begins. Because notice that this delta X is supposed to be the thickness in the direction of heat transfer of that conductive element. But this thing is infinitely large, right? So this blows up to infinity. The thermal resistance here is infinitely large. Is that a problem? Yes, because if you consider the thermal circuit equation, having this be infinite tells you, hypothetically speaking, that you can have a zero heat transfer rate and still sustain a difference in temperatures, right? That there can exist a difference in temperatures without there being heat transfer or flow of heat, which is totally contrary to what we had initially assumed was the entire point of the field of study of heat transfer, that differences in temperature lead to the movement of heat. And so clearly, this doesn't work. That's weird. How can it not work? We've run into what I like to call the thermal paradox at infinity. And this is an issue that happens whenever we are dealing with large systems and trying to use the equations that we use to model heat transfer within systems, right? Because remember where this came from. This all came from trying to create an equation that tells us what heat transfer inside of objects looks like. And if I had, modeled this thing, rather than being, some kind of like infinite planar surface, maybe some kind of like weird contrived infinite cylindrical section, we'd still run into the same problem, right? Assuming that that section was large. For any semi-infinite system, the thermal resistance given by the conductive derivations that we would have to do to get it will always be infinitely large. And so as a result, this is not okay. So can we try to trace what makes it not okay? Sure. I mean, this is a planar system, right? So we can try to model what the temperature looks like inside of this thing. And we know that under the 4 assumptions that we had applied before, that the equation that governs the temperature profile as a function of x from the surface of the soil all the way down to, infinitely far down into the soil is this. And this is just saying the second derivative is 0, which is implying that the temperature of the, soil as a function of how deep we are in it is just a line. Okay? And that by extension, the rate of change of that temperature is a constant, which is just C1. Now, what is this? What is the issue here? Well, consider the fact that if the temperature changes constantly over space, regardless of what the value of C1 is, any number other than 0 is going to give us a temperature that either blows up to infinity or negative infinity as we get further and further down into the soil. But we know that that can't be the case because the temperature at infinity is just T soil. It's a fixed number. It's a finite number. So the only thing that will work is to say, well, C1 is 0, right? Kind of similar to considering the temperature profiles inside of cylinders. But if we do that, we're left with a constant temperature profile inside of the soil. And if there's a constant temperature everywhere, right? If there's no temperature gradients, then that means no heat transfer is happening in the soil, which is also incorrect. So what's happening? What's happening, the reason for this thermal paradox is that we've created a set of assumptions to try to model the system, which because of the semi-infiniteness of it, cause them to not be self-consistent. Like one of these assumptions has to fail. And most commonly, the one that fails in this sort of analysis is the steady state assumption. And think about it, right? This thing is an infinitely large slab of soil. Imagine the amount of time that it takes for this slab of soil to heat up or cool down, right? Can this slab of soil even ever really reach steady state? And that's a perfectly valid question. We can also ask ourselves, if this thing is infinitely large, is it actually true that the K is not going to change, right? I mean, we know that K in general could be a function of all kinds of things, including temperature. So maybe the fact that the K changes also contributes, right? That the assumption that this is just a single number fails whenever we have a sufficiently large system. And what you'll find is that in real systems, it's a combination of both, and that the way that we have to model the temperature profiles of these things is based entirely off of theoretical analyses that we can't really understand by using thermal circuit assumptions or even, anything within the wheelhouse of stuff that we're going to learn in this course. Most of the time when people work with semi-infinite systems, when they're trying to understand what the temperature of this looks like, they have to resort to a table that's usually listed in heat transfer textbooks that tell you, oh, if this is the temperature, if this is this temperature, if these are the material properties, then this is what the temperature profile is going to look like. And it's written down in a table and derived, using very complicated mathematical analysis that was done 20 or 30 years ago, and then off you go, right? But there's no actual solving process. We're just relying on those analytical tools or on empirical data, okay? So this seems like kind of a not very satisfying ending. Like basically I'm just showing you the system and telling you like, oh, this is actually not going to work. But think about something interesting. Why haven't we tried to understand what the temperature profile looks like inside of the air in the previous exercises that we've done? Why can't we try to use the same equations that we used to model the temperature changes inside of the soil, to model the temperature changes inside of the fluid. It's because every single system that we've worked on before, when we've been talking about the fluid, we assume that it's a semi-infinite system, right? That the air or the water or the fluid that's surrounding the object of interest is infinitely large, and that the temperature T air is just this asymptotic temperature. And so if we tried initially, if we had tried to use the heat equation to understand what the temperature profile in the air looked like, the set of assumptions that we usually applied would lead us to the same paradox that we're hitting now. But notice that because we've been modeling the air using this heat transfer coefficient, right? Because we've just said, well, jam all of the physics into the heat transfer coefficient and then forget it. That process has actually avoided us running into the paradox that we just ran into with the conductive element. And it also tells you retroactively why it is that we model heat transfer between a solid and a fluid using this, right? Using an H, instead of trying to use, a set of like conductive resistances where we could just define a K for the air and then just try to solve it that way, because we'd run into the same issue. And so this is one of the interesting things that tells us, again, retroactively, the philosophy of how we study heat transfer, which is that, we set up the equations in such a way that they work for us, right? Even though, not necessarily speaking, even though we find that trying to set up a conductive analysis of the air wouldn't work, we nevertheless can consider some asymptotic temperature T air. And we can measure some temperature of the surface of a soil. And that we can do an analysis by experimentally measuring a heat transfer coefficient, and then off we go, and then we're good, right? So the point of this is that this feature, this avoidance of the paradox, is the entire reason that we model convection using the model that we developed for analyzing heat transfer between objects, instead of using the model for analyzing heat transfer within objects. We obviously have a lot more to say about this, but we will talk about that when we actually start talking about convection and what is so-called the problem of convection in the following lectures.